Hey guys, my name is Hiraku Murakami. I'm here with NovaEdge Academics, and today we'll be continuing with part 3 of B5, Current and Circuits. We're going to start off with talking about EMF and internal resistance. So just to recap, we've talked about, what voltage means, what resistance, current means, and all the circuit kind of problems that we did in last video. So let's talk about EMF and internal resistance. EMF is just another name for voltage. It's electromotive force, and it applies to, when we talk about a battery. So when we say, a battery has this much EMF, we're saying that the battery has this much voltage. But we'll never say a resistor has this much EMF, because that's just not how it works. A resistor does not have an electromotive force, right? It's a battery that's pushing the current. So that's the reason why we differentiate them. And internal resistance is the inherent resistance within batteries, because within batteries itself there's also a resistance. So that's just something that we haven't talked about before, but now we're talking about it. So you can see in this diagram, like this is a shape as a battery, right? But within the battery you can have a resistance, okay? So how does this change the calculations? Well, it actually doesn't really. Like, it just, you basically consider like you have another resistor in the circuit, and then you just calculate based off of that. So nothing too complicated. Just imagine this internal resistor is outside the battery. It's just in series with whatever that's outside. So if I have a parallel circuit here, then I'm going to basically have two parallel resistor connected in series with the internal resistor. Okay, now you're gonna see this equation. It's important to understand the equation. It's just saying that it's the EMF is equal to the current times it by the sum of the resistance of the circuit. So EMF is equal to I times by external resistance in the circuit plus by internal resistance. So you're just adding this with this to find the EMF. That's just it. So it doesn't really do anything. If I were to try to find the total current of the system, I would still have to calculate this plus this divided by the voltage, right? So nothing changes in terms of calculations. Just consider another resistor in series. That's it. So we're going to do a few problems anyway. So let's do this one. So we've already done this before, right, in the last video. So if you haven't checked that out, we're just adding an internal resistor of 1 ohm. So what change does it bring to the entire thing? It's just you add another 1 ohm resistor in the circuit. So let's calculate the total current. To find the total current, we always find the total resistance. So resistance total is going to be equal to this plus this plus this. This is just 1 over 2 plus 1 over 3 inverse. And we already calculated this, right? So that's just going to be 6 over 5. So that's 1.2 plus 1.8 plus 1.0, which is 4.0 ohms. Okay? Now, to calculate the total current, that's just V total over R total, which is 6 volts over 4 ohms, which is 3 over 2, 1.5 amps. That's it. Without this, it was actually 6 over 3, which was 2 amps. But because we account for the internal resistance, it becomes 1.5 amps. That's it. So it doesn't really change. As you can see, it doesn't really change the calculation that much. You just add a resistor in series and you account for it. That's it. Okay? Now let's talk about electrical power and what that means. So first, let's recall the definition of voltage. And if you remember, the definition of voltage was work done per charge, right? So it's joules per coulomb. Okay? So rearranging this, you get QV is equal to W. But also recall in general, in kinetics, right? We said the power is equal to work over time. This is something we've been consistent throughout topic A and B, right? Whenever you say power, it doesn't matter if it's mechanical power or thermal, whatever, right? Power is equal to work divided by time, okay? So let's incorporate this in terms of electrical. Well, we know work is equal to this. So QV over T. We also know actually that Q over T, that's current. So essentially speaking, power is equal to current times voltage. That's actually it. I'm just showing you the derivation so you can see that it makes sense, okay? So power is just current times voltage. Remember, using Ohm's law, I can shift this around. So V is equal to IR using Ohm's law, right? So I can just change this to IR. So that's I squared over R. I can also, try to replace I with V over R. So if I plug this expression in here, what do I get? I get V over R times V, which is V squared over R. So power is equal to IV, also equal to I squared R, also equal to V squared R. Why am I saying all of these different formulas? By the way, these are all in your data booklet. Why am I saying all of this? Because, well, if you know I and V, you should just do P is equal to IV. If you know I and R, you should just do I squared times R. If you know V and R, you can just use this. You don't have to go one more extra step to, try to convert it to the things that you want to use. Okay? Now in practice though, I always forget these two. I always remember VI. Okay, so I always just convert it to voltage and current and calculate power from there. Okay, that's just me in my practice. So let's do a practice problem. So let's find the power within all of these resistors. So we've already done a bulk of the work, so we know R total is equal to this plus this. So 1 over 2 plus 1 over 3, this plus 1 over 8, 1.2 plus 1.8, 3 ohms. I total, of course, 6 over 3, 2 ampere. We also know current here is also 2 ampere because this is in series with this and this, right? So in series we know current stays the same. So let me call this 1, 2, and 3. So I1 is equal to 2 ampere, R1 is equal to 1.8 ohms. So let's just find VI. VI is I1 R1. So 2 times 1.8, 3.6 volts. Now power in the first one is equal to I1 times V1. So that's 2 times 3.6, 7.2 watts. Perfect. So now I know this is 3.6 volts. I know that these two, both of them, V2 is 6 minus 3.6, 2.4 volts. V3 is also 2.4 volts. By the way, at any point, if this is confusing, just watch my previous video where I've walked you through this exact problem, okay, the exact problem. So if you're confused about this, go take a look at that one. It's a lot more detailed in explanation, right? So I also know R2 is 2 ohms, R3 is 3 ohms. I actually don't even need to calculate the current. I could just say that P is equal to V squared over R. So I can do 2.4 squared over 2. That's 2.88 watt. Let me bring this a bit this side. Right, and P3, same thing, 2.4 squared over 3, 1.92 watt. Okay, so that's basically it. So electrical power is, you can use this and find the electrical power in all of the resistors. Okay? By the way, if you want to talk about the power of the battery, you can also do the same thing. I know the current is equal to 2 ampere, right? So 2 ampere times 6, that's 12 watts. Okay, let's do another practice problem. All right, A, part I, the current is equal to V over R, 12 over 240, which is 0.5. Sorry, 0.05. Okay, part 2, the power is equal to VI, 12 times 0.05, which is 0.6. Part 3, the total energy transferred in 2 minutes. Well, power is joules per second, right? So if I do power times time, 0.6 watt times it by the time, 2 minutes, so that's 120 seconds, I get 72 joules of energy transferred. B, what value resistor would have twice the power with the same voltage? Okay, I know P is equal to V squared over R. So if I keep the voltage and change resistance to have double the power, I need to decrease by 2 to increase by 2. So half resistance to lead to double the power. Okay, all right, let's do C. So C, they're asking for now, okay, how about we maintain R and change V? How much do we need to change V to double the power, right? So same equation, P is equal to V squared over R. R is constant, so we can ignore that. So what do I need to do in order to 2x the power? Well, this is about proportionality. And you need to be careful with this because V is squared, right? So if I double the voltage, what happens? If I double the voltage, then I need to do 2V squared over R, which is actually 4V squared over R. And this is the original P, right? So I'm actually quadrupling the original power by doubling the voltage. I don't want that. So I actually need to be careful and actually only do square root of 2. Because if I do square root of 2, factor of square root of 2, then that leads to square root of 2 times V squared over R, which is actually 2V squared over R. And this is equal to P, the original power. So now I'm doubling the power. Okay, so the correct answer is you need to multiply the voltage by a factor of square root of 2. Okay, let's do another practice problem. Pause the video and give this one a try. Okay, so very simple. Calculate the resistance that would be needed to make that. Okay, so R is equal to V squared over P. So 110 squared over 1.25 times 10 to the power of 3. 9.68 ohm. Okay, part B. What current flows through the heater during normal use? Well, P is equal to IV. Isolate I get P over V. Very simple stuff. Alright, so that's 11.36 ampere. Hey guys, thanks for watching. If you like this kind of video, then consider giving us a like and subscribing to our channel. We have a lot more lecture style video and content like this in our channel, so feel free to go check it out. If you're looking for additional guidances like one-on-one tutors in IB subjects, SAT, TOK essay, IAs, writing, etc., then go to our website at NovaEdgeAcademics.com, fill out the form, and get in touch with us. In the meantime, we'll see you in the next video.